Welcome back. As we expand on our strategies for evaluating different types of integrals and different forms of integrals, we're going to continue looking at trigonometric integrals, specifically when we are dealing with powers of sine and powers of cosine. In the first and second videos in this series, we looked at where the power of sine was odd. Second video, the power of cosine was odd. In this video, we're going to look at case 3 where neither of those situations occur. Okay, so m and n, both of those values are even powers. And we'll look at how to attack this type or this form of integrand and how to integrate it easily. This is going to be probably the longest of the 3 videos in this series, evaluating our case 1, the power on sine is odd, case 2, the power on cosine is odd, and then case 3, both of those powers are even. So how do we deal with case 3? M and n are both even. So what we're going to do is we're going to use some double angle substitution. We have 2 double angle formulas that we use here. We have sine squared of x is 1 minus the cosine of 2x divided by 2. Or we would use cosine squared x, which is equal to 1 plus the cosine of 2x over 2. And both of these are derivations of our double angle identities for sine and cosine. So we use these 2 formulas to reduce that integrand to one in lower powers of that cosine double angle. All right, so we're going to do some substitutions here. Let's look at an example. For this example, you'll notice that both my power on sine and cosine are even. We need to integrate sine squared x times cosine to the 4th x with respect to x. So we're going to use both of those double angle substitutions I just mentioned on the previous screen. So one thing we know is that sine squared x, that's going to be 1 minus the cosine of 2x over 2. And cosine squared x, keep in mind that to the 4th is something squared, right? So this can be written as 1 plus the cosine of 2x over 2, that quantity squared. All right, so thinking about this, I have a 1/2, I can pull that in front, and here squaring that 1/2 is a 1/4. So pulling out 1/2 times 1/4, this is going to give me 1/8, the integral of 1 minus the cosine of 2x times 1 plus the cosine of 2x squared. So go ahead and pull that fraction part out. Now you'll notice that everything is now in terms of cosine. So that's a little bit simpler. And I can multiply this all the way out, make it look like a polynomial. So I'll square this binomial and then I'll FOIL distribute through here. And with some repeated multiplication, that gives me 1/8, multiplying all of that out. I'm going to skip that step. 1 plus the cosine of 2x minus cosine squared of 2x minus cosine cubed of 2x dx. So I FOILed this binomial. I got 1 plus 2 cosine 2x plus cosine 2x quantity squared, and then I took those 3 terms, multiplied it by these 2. I end up with this polynomial-esque looking piece here. So this first one, that's easy for me to integrate. I know how to integrate that. I'll get x. Here I'll integrate this and get sine of 2x over 2. You either know that pattern or you do a quick U substitution. And then we have to look at our second and third terms here. Second, we have cosine to an even power, We can do a similar substitution as what we just did up here, and that will allow us to break it down. And then we will do this piece. This is cosine to an odd power. So we'll do that the same way we did in the video before this. All right, so I have 1/8 times, integrating this first term, I get x. Integrating this second term, I have plus the sine of 2x over 2. So I still need to deal with my integral for cosine squared of 2x dx and minus my integral for cosine cubed of 2x dx. So looking at my two integrals I have left, I'm going to do each of those separately. So for this piece, the integral of cosine squared 2x dx, I'll use my double angle substitution. Now notice my double angle substitution, if we go back a page here, we went from 1x to 2x. We doubled that. So looking at where we are now, this is going to become 4x. So this is equal to the integral of 1 plus the cosine of 4x over 2. Pulling that 1/2 in front, I have the integral of 1 plus the cosine of 4x dx. Each of these terms is fairly easy for me to integrate. I end up with 1/2. 1 turns into x, and the cosine of 4x is the sine of 4x over 4. And of course we have plus some c values. Since I'm going to have multiple integrations and multiple c's, I'm going to call this c sub 1. So distributing that 1/2, I have got 1/2 x plus 1/8 of sine to the 4x plus c sub 1. This value, I'll scooch this down, this value can go right in here for that integration. All right, so this at the bottom that I've just calculated, the 1/2 x plus 1/8 sine of 4x plus c sub 1, that's equal to the integral of cosine squared 2x. All right, so we have one other piece, which would be this last piece. I'm going to kind of draw a divider here. We're dealing with the integral of cosine cubed of 2x dx. So this is case 2. Cosine has an odd power. So we think about writing that 3 as 2 plus 1. 2 times 1 plus 1. Remember my 2k plus 1 format. So unmultiplying, in a sense, I've got cosine squared 2x times cosine 2x dx. So for my squared piece, I'm going to sub in a Pythagorean identity. This is 1 minus sine squared of 2x. So that substitution I just made goes for cosine squared 2x. That's equal to 1 minus sine squared of 2x. So we're left with cosine of 2x dx. And I'm going to work this a little differently than I did in the previous example. If I let u equal the sine of 2x, well, then the derivative of u with respect to x is 2 cosine 2x, or rather 1/2 du equals cosine of 2x, I'm running out of space, dx. So this right here is going to equal 1/2 du. So my integral is 1 minus, I have u squared times 1/2 du. And this is now easy for us to integrate. I have 1/2 the integral of 1 minus u squared du using my power rule. I'll get u minus u cubed over 3 plus c. And since I have multiple c's, I'm going to call this c sub 2. So remember, u is equal to sine of 2x. So this is 1/2 times the sine of 2x minus 1/6 times the sine cubed of 2x plus c sub 2. So this value that I have found, I will be able to plug in right up here for cosine cubed of 2x. So I'm going to go to the next screen and I'm going to just write out what we have. So this is what we had written out. 1/8 times x plus 1/2 of sine of 2x minus the integral of cosine squared of 2x minus the integral of cosine cubed of 2x. And so I wrote both of these pieces. I worked them out in some scratch work. I have 1/8 x plus 1/2 the sine of 2x minus the integral of cosine squared 2x we said was equal to 1/2 x plus 1/8 the sine of 4x minus the integral of cosine cubed of 2x was equal to 1/2 sine of 2x minus 1/6 sine cubed of 2x. And of course, running out of space, but I've got a plus c. So I'll just use a regular c here. So we had some interim arbitrary constants, c sub 1 and c sub 2. And when I add up all of these different arbitrary constants, I'm going to end up with just some other arbitrary constant. At this point, we are completely done with our integration. Put a little end bracket there. We're completely done with our integration, and we just need to distribute combined like terms. So the first thing I'm going to do is take this 1/8, multiply it through, also distributing some negatives as I go. So I have 1/8 x plus 1/16 sine of 2x minus 1/16 x minus 1/64 sine of 4x minus 1/16 sine of 2x minus 1 over, that would be a plus 1 over 48 sine cubed of 2x and plus c. All right, so that negative distributed, made this negative here distributed, turned that positive, and of course the 1/8 went in front of all of these coefficients. So a couple things we'll notice. We have some terms that cancel. 1/16 sine of 2x, positive and negative, those are going to add to 0. 1/8 minus 1/16, that's going to give me positive 1/16 x minus 1 over 64, the sine of 4x plus 1 over 48 sine cubed 2x plus c. Essentially, we are done, but you may notice that all three of these terms have a GCF of 1/16. I always recommend factoring that out. So I have 1/16 x minus 1/4 sine of 4x plus 1/3 sine cubed of 2x and plus c. So that would be my final answer here. So we did a trig problem that had two other mini trig integrals hiding in it. So I hope that helps. I hope you have some experience. Again, not always do you have to use these strategies. And sometimes you may get slightly different answers if you use a different strategy. And those answers would give you a value that's close, but could be off by an arbitrary constant. Email me if you have any questions. I believe I have one more video, maybe two in this series.